Yo, have you ever wondered that if Hogwarts were a bit more advanced and they had computers, how would the students develop programs to run on them? They would probably find it very difficult to understand the programming languages we muggles use like C, Java, Haskell, Python, and etc. But what if we give them a new programming language which is specifically designed for wizards and connected directly to their magical spells? If you think about it, programming is no different than magic. We use a certain sequence of words to tell the computer what actions to perform. Any programming language is just plain text, which, when passed into a compiler, gets translated into assembly or binary code that the machine can execute. In this series of videos, we will learn how to design a compiler, which is one of the most difficult problems in whole computer science. It took about 18 years to solve this problem. In this video, we will just get a brief overview on the theoretical part of how to build a compiler. The process happens in mainly 3 steps. Lexical analysis. In this way, the compiler breaks the plain text, which is supposed to be our programming language, into smaller pieces called tokens. Each token represents a meaningful element like a keyword or an identifier or operator like plus minus, or a literal which is inside a string double quotes. For example, in our programming language, a spell like lumos and bracket, we enter a string hello world, which will be broken into lumos, and we classify it as a function. Then the left parenthesis as a left parenthesis, hello as a string literal. We classify all this so the compiler can read the whole tokens properly. Then we pass this to the syntax analysis, which is also called parsing. After the lexer products token, the parser checks whether these tokens follow the grammar rules of the language. Like, for example, every language has some grammar. Like in English, we can't say follower me. Most famous technique used for syntax analysis is a syntax tree. We generate a syntax tree, and then we use a method called recursive descent, which recursively searches the tree to find the correct logic. In our series, we will use, of course, the syntax tree paired with code generation. We will directly generate assembler code, our language will be faster than Python. To make our wizard language efficient, we can implement explicit type declarations, unlike Python, where the interpreter automatically checks variable types at the runtime, which slows down the execution slightly, not a lot. In our language, the wizard must define the type of the variable, like integer and the variable name. So our compiler knows that it's an integer and it doesn't have to check. So the code will be a bit faster. Not a bit, it will be decently faster. So code generation will happen faster and we won't have to perform runtime type check. In the 1900s, when compilers were just becoming a thing, the computers have had very less storage. So they used a technique called this. They stored different components of a compiler in different storages. Like one storage had a lexical analysis component, one had a syntax analysis, one did the code generation, the assembly code or binary code. So in that time the storage was very less, but we have at current moment we have a lot of storage. We can of course code it in one file. Basically, lexical analysis and syntax analysis are very trivial parts of compiler design. The most important parts are code generation and the recursive descent parsing. Recursive descent is a top-to-down parsing technique used by compilers to analyze the structure of a program. It's the most famous one that people use. Even Jack Crenshaw in his book used this technique. And it's called recursive because it calls its own function many times in its own function. Good analogy to explain recursive descent can be like you are reading a book. It has multiple titles. You read each line one by one. You stop at a title and read the entire content. If there is a mini title inside it, you read it first and then move ahead. Similarly, recursive descent does the same. It reads the whole plain text one by one, then converts into syntax tree and then generates our code. Assembly or binary, of course we will use assembly in this one because binary will be a bit more, it will be too much detailed. If you want detail, you can read the Dragon book. We will start by defining a set of rules for our programming language. Like every programming language has a grammar, a set of rules that tells you which sequences of tokens are valid. Like for example, we will define an identifier for a function call or a argument list. Like there is a list in Python, an array in Java, and an empty argument. Then we will write a function for each rule. Like to parse function call, we will write one. To parse an argument list or an array, we will write one function. The parser reads tokens in order and calls the appropriate function based on the grammar. Like for example, to print some statement, we will use lumos and bracket, then double quotes, and we write a string. The parse function call sees lumos, it's a valid identifier, it consumes it. It sees the left parenthesis, then consumes it, then calls the argument list again to fill in the arguments, the string inside it. It sees like hello world and consumes it. Then it sees the right parenthesis and it consumes it and it finishes. You can see the parse argument list calls itself many times to handle multiple arguments. This is called recursion. We will also build an error handling system. Like for example, if the system doesn't sees a semicolon at the end, it throws an error. A semicolon is an easy way to handle with when a statement is getting terminated and when it gets stuck. As the parser consumes all the statements in the plain text, it builds a tree representation of the program called the abstract syntax tree. The nodes of the tree represent the functions, arguments, or operators or variables. Later we have to search this AST for semantic checks and code generation. Now from the next video we will start writing all the components of our compiler. Bye.